ご案内いたします。まもなく京都賞記念講演会を開会いたします。会場にご入場、ご着席の上、お待ちいただきますようお願いいたします。繰り返しご案内いたします。まもなく開会いたします。会場にご入場、ご着席の上、お待ちいただきますようお願いいたします。Ladies and gentlemen, thank you for waiting. The Kyoto Prize commemorative lectures will begin shortly. Please be seated in the main hall. The Kyoto Prize commemorative lectures will begin shortly. Please be seated in the main hall. Thank you.
大変長らくお待たせをいたしました。ただいまから第35回京都賞記念講演会を開催いたします。私は本日司会を担当いたします徳田明でございます。どうぞよろしくお願いいたします。ありがとうございます。さて、京都賞でございますが、1985年、昭和60年の第1回から今年で35回目を迎えました。今年の京都賞では、ご案内のように、まず先端技術部門、材料科学の分野からは、2層からなる有機 EL 素子構造を考案し、発酵効率が高く、低電圧で動く素子を初めて実現するとともに、構成材料や素子構造の改良で、さらに性能を向上できることを示した陳 W. 丹博士。基礎科学部門、地球科学及び宇宙科学の分野からは、広大な領域の3次元デジタル宇宙地図を作るスローンデジタルスカイサーベイ計画の構想、機器開発、データ解析など、ほぼすべてにおける指導的役割を通じて、宇宙の進化史解明に貢献されているジェームズ・ガン博士、そして思想芸術部門、映画・演劇の分野からは、創立をした太陽劇団とともに、歴史と政治を主題にする国際的評価の高い傑作を生み出し続けておられるアリアーヌ・ムヌーシキンさん、こちらの3名の方々が選ばれました。本日はこの3名の受賞者から輝かしい業績と長年にわたってのご経験に裏打ちされたお話が伺えるものと存じます。それではご講演に先立ちまして、主催者を代表いたしまして稲森財団理事長金沢忍よりご挨拶を申し上げます。
皆さんこんにちは、金沢でございます。本日は第35回京都賞記念講演会にご参加いただき、誠にありがとうございます。心より御礼申し上げます。本年の京都賞は、先端技術部門で、香港科技大学 IAS 東亜銀行教授、ロチェスター大学名誉教授の陳 W. 丹博士、基礎科学部門で、プリンストン大学名誉教授のジェームズ・ガン博士、思想芸術部門でフランスの太陽劇団創立者主催であるアリアーヌ・ムヌーシュキン氏が選ばれ、昨日京都賞が授与されました。この京都賞は、人のため、世のために役立つことをなすことが人間として最高の行為であるという財団創立者稲盛和夫の理念に基づき、真摯に努力を重ね、その素晴らしい業績をもって人類社会に貢献された研究者や芸術家の方々を顕彰するため、1984年に創設いたしました。テクノロジーや自然科学の分野を対象とする先端技術部門と基礎科学部門、哲学倫理などの思想や音楽や美術等の芸術活動などを対象とする思想芸術部門の3部門で毎年検証を行い、これまでに111名と1団体をこの京都にお迎えいたしました。創設以来35年を経て、京都賞は国際賞として各所より高い評価を頂戴できるまでに育ってまいりました。これもひとえに私どもの理念を深くご理解いただき、公平・厳正な審査を重ね、素晴らしい受賞者の方々をお選びいただいたご専門家の方々、そして常に温かくご支援いただいております皆様方のご協力の賜物と心より感謝申し上げます。本日ご講演いただく3名の方々は、人類を代表する知性の持ち主であり、その高い倫理観と実行力においても傑出した私たちのお手本ともなるべき方々です。ご専門もお立場も異なりますが、それぞれの人生観や世界観を通してのお話は、私たちの心を高め、人生に大きな影響を与えうる示唆に富んだものです。その形骸に接することで、ご来場の皆様方が 新しい気づきを得ていただければ、私どもにとりまして、これほど嬉しいことはございません。稲森財団では、この京都賞をはじめとして、若手研究者への研究助成事業や、未来を担う若者や子どもたちに向けた教育活動、また講演会や芸術講演の支援など、さまざまな社会啓発事業を行っております。今後もこうした事業を通して、国際相互理解の増進に努め、人類の平和と繁栄に積極的に貢献するため、一層努力を重ねてまいります。最後に、本日ご参加の皆様に改めてお礼を申し上げますとともに、この講演会が皆様にとりまして、実りを多い有意義な会となりますことを記念申し上げ、ご挨拶とさせていただきます。ありがとうございました。
ただいまの理事長の挨拶にもありましたように、この講演会はより多くの方々に3名の受賞者の人生観やあるいは世界観に触れていただくための催しでございます。本日はまず各受賞者の横顔をスライドでご紹介して、その後ご講演をいただこうと思っております。なお、お二人目のジェームズ・ガン博士のご講演の後に休憩を取る予定にしております。あらかじめご案内を申し上げます。今日最初にご講演をいただきますのは、先端技術部門で受賞された陳 W. タン博士でございます。では、タン博士、ご入場ください。それではご講演に先立ちまして、タン博士の横顔をご紹介いたします。ステージのスクリーンをご覧ください。
陳 W. タン博士は1947年、香港でお生まれになりました。お母様との一枚です。お母様は家事を切り盛りしながら子どもたちを大事に育てられました。商工会の会頭をしていたお父様は、小中学校の設立にも熱心に取り組み、地域のリーダーとして尊敬されていました。博士は小さな頃から好奇心旺盛で、身の回りにある道具の仕組みにとても興味がありました。よく農作業の道具を組み立てたり修理したりして、その仕組みを勉強しました。高校生になった頃から興味は科学へと向かいました。アメリカのコーネル大学で物理科学の博士号を取得しました。その後、イーストマンコダック社に入社した博士は、有機 EL の持つ可能性に着目しました。有機 EL とは、有機物に電流を流すと発光する現象で、この現象を利用した素子が有機 EL 素子です。最近はスマートフォンやタブレットなどのディスプレイによく使われていますが、博士が研究を始めた頃は、非常に高い電圧をかけてもわずかに光る程度で、実用化には程遠いものでした。1987年、博士はそれまでとは一線を画する有機 EL 素子の構造を提案しました。有機物の膜を非常に薄くすることで電気抵抗を下げ、さらに2種類の異なった有機物を2層構造にすることで、低い電圧で効率よく発光する素子ができました。研究を重ね、より効率よく発光させ、また光の色をコントロールすることができることも示しました。 これにより実用化への道が開かれました。博士の発表は当時行き詰まっていた有機 EL の研究開発のブレイクスルーとなり、世界中で研究が活性化し、実用化が飛躍的に進みました。現在はスマートフォンやテレビの高精細ディスプレイとして普及し、今後も社会のさまざまな分野に応用されていくものと大いに期待されています。博士は現在も有機 EL の可能性を求めて研究を続けています。また次の時代を担う研究者の育成にも力を注いでいます。博士は若い人たちへ自分の得意分野に情熱と忍耐を持ってひたむきに取り組んでくださいとアドバイスをくださいました。博士のご家族です。奥様も物理科学の博士で、長年大学で教鞭をとっていました。今年で結婚40年になりました。大好きな京都で過ごす奥様とのひとときを楽しみにされています。
本日、譚博士にはご自身の人生を振り返りつつ、有機 EL 素子が博士の発見から今日の製品となるまでどのような発展の道をたどってきたのか、それについて語っていただきます。演題は有機 EL ディスプレイ技術の進化です。それでは譚博士、お願いいたします。
I would like very much to thank the Laureate Foundations for giving me such a deep honor. Today, I'm going to talk about the evolution of OLED display technology. OLED stands for Organic Light Emitting Diodes. In many ways, it's a journey of my life. So I'm going to tell you a story. I'm from the Hong Kong University in Science and Technology. I've been there for 5 years. So my own revolution, just very briefly. I came from Hong Kong. Hong Kong is in the south of China. It's a very small place, measuring 20 miles by 20 miles. Hong Kong, as you know it, as most of you know it, is a very bustling city. It's a city of lights, beautiful lights at night. But Hong Kong in the last couple of months is very chaotic, in turmoil. I'm sorry to say that, but I would like to ask for your support and understanding of the Hong Kong situations. And I also would like you to come to visit, if not now, in the near future. I came from a town in the northwest part of Hong Kong called Yunnan. And in the 50s, Yunnan was quite a bustling town. The main street, as you see here, was lined up with shops, restaurants. The villagers from nearby villages would come there to enjoy the morning tea or sell their goods. And that's the place where I grew up. I actually grew up in the village, nearby. And today, I moved to the the southeast to a university is only 25-year-old, and continue to do my research there in organic LED and other subjects. So, my village, and this is my the house built by my grandfather in 1921, almost 100 years ago. It's still standing there, and the reason it was standing there because it was made of very good materials, the bricks. The bricks was actually made in the kiln that owned by my grandfather. So he probably chose the best bricks and built the best house for himself and his family, and that's why it's still standing today. And nearby we call it our old house, is the village shrine. It's a one-room building with a very small room attached to it. The small room is a one-room schoolhouse where I first have my first taste of education, 5-year-old. And I probably spent a few months there learning very simple Chinese. But that's how I started in my education pathway. So my early educations, I went to a primary school from 1953 to 59. The school was built in 1951. And my father, who is very influential in the town, particularly in education matters, that was responsible, the founding father of members of the school board. So he was a very important person to the community and also a very important person to me. But he also had very wild connections. And as you can see here, he was with Richard Nixon, the Vice President of the United States. I don't know how that he could invite the Vice President of the United States to visit his primary school in a remote place in Hong Kong. He was pointing to Richard Nixon. I think he was telling him what to do at that moment. I'm not so sure. But my family has very special connection with the President of the United States. Not only my father had a chance to meet with the Vice President who later became the President of the United States. And here is my son. He had a chance to meet with President Obama. That was in 2011, when Obama was running for re-elections. I'm sure my son has something to do with his being re-elected. Again, I'm not so sure. So my father's generation, my son's generation had a chance to connect with the President of the United States, but my generation, no. So moving forward, after leaving Hong Kong, I went to the University of British Columbia in Vancouver, Canada, to study chemistry, and where I had the opportunity to do research and beginning to do research with Professor Grislow. I don't know how I got into research, but I was very interested in building things. I was very proud of myself to build a piece of equipment out of glass, doing glass blowing all by myself. So I thought I would, I could make a living as a glass blower, but I'm glad I didn't do it. I moved on to higher educations. So after 3 years, I moved on to Cornell University to study physical chemistry under Professor A.C. Albrecht, and we call him Andy Albrecht. Of course, I learned of sciences from him. He's an expert in molecular spectroscopy. So I learned a little bit of spectroscopy some solid state physics, and under his directions. But he really did not direct me to do experiments. He just there for me to ask questions, if I need to ask questions. He's trying to train you to be independent researchers. But most importantly, he taught me how to be a good human being, the humanity, and with a strong tilt towards liberalisms. So he taught me to read the New York Times. It's probably the most liberal newspaper in the world. Then I went to Kodak right after the graduate school. I spent 31 years there. And as you can see from this picture, I really enjoy my work, and I was quite happy there. And after 31 years at Kodak, I moved on to academia. I was fortunate to have the opportunity to become a faculty member in the Department of Chemical Engineering in the University of Rochester, and then following that, coming to Hong Kong to be with the Institute for Advanced Studies at the Hong Kong University in Science Technology, where I'm still there now. So that was my very quick personal evolutions. Now I'm going to tell you the evolution of display technologist. So in this diagram, the horizontal axis is the year, starting from 1950 to 2030, projecting into the future. And then on the vertical axis is the dimension of the display in inches, the diagonal of the display. So the small display can be as small as less than 1 inch, and the big display, like this one, can be hundreds of thousands of inches. So in the 1950s, all we had were cathode ray tubes, big boxes. And that technology kind of lasts almost like 50 years. And until 1990 or so, the people want to have bigger televisions. But then they're getting heavier and heavier and heavier. You cannot even get into a small apartment. So the technology has to be replaced. And also, at the time, there was an evolution in computing. So portable computing is very important. So we had to come up with a technology that allows you to be portable. So that's where the flat panel display come in. So the CRT become obsolete, and then the flat panel display start coming in. And there's quite a few flat panel display technology. All I'm going to talk here is the LCD. So the LCD can be made small and also can be made very large. For the small one, they were used for the cell phones, the laptops, below 10, between the several inches to tens of inches. And they can also make very large TVs, typically on the order of 55 inches, 65 inches, or even bigger. So I put it, say, below 100 inches. And OLED, which come in about 2010, so that's about almost 20 years after the LCD. OLED find that the technology can be used for both the small display as well as the big display, just like the LCD. So OLED really was here to compete with the LCD because LCD is already existing. And as I will tell you later on in my talk, the competition is going quite well for OLED. And OLED has also another features, which is that it can be folded, it can be rolled, and so on. It can be curved. So it has a form factor which allow you for newer applications, like something that you can wear, like the watch and the other display as well. More recently, just in last year or two, there's another technology that came along, and that is called the micro LED light emitting diode. And this is based on inorganic gallium nitride materials. And that technology, because you can tile the display together without the seams, and so we can make as large as you like, as you can afford to pay for it. And that display technology, the one at the upper corner there, almost have no limit in size. So they can go to 1,000 inches, more than 1,000 inches, but they cannot go small. So at least not now. So OLED and LCD can compete very well against each other, and we don't have to worry about the micro LED competing in the small dimension displays. So because CRT is such an important technology, even though it was obsolete now, I want to just briefly mention how the discovery came about. First of all, there is a discovery of electrons by J.J. Thomson back in 1985. And he was given a Nobel Prize in 1905 because of that. Just imagine discovering the electron, which we use for the electricity today. And then a few years later, Karl Braun used the electron to hit a screen that has a phosphor on it, and so that you can produce an image on the screen. And that's how the CRT2, or the modern TV, was the first discovered. So he won a Nobel Prize in 1909, but not for the display that he invented, but for a telegraph. So you can see, if you're smart, you can do many things and still get a Nobel Prize. So that was the CRT. So the problem with CRT is that it's very heavy and very thick, just because the technology was based on one electron gun. Okay. In other words, you have one addressing element for all the picture element we call pixels on the screen. And the screen can have 1 million pixels, but you have only one gun. So the gun has to be directed to the screen using a magnetic field or electric field. So in this CRT technology, the thickness is proportional to the screen size, and the weight proportional to the screen size. And so the limitation is that it cannot be scaled to large screens. Here comes the flat panel display technologies. The difference there is that for each addressing element, you have 1 pixel. So you can compact them into a flat screen, as shown in this diagram on the right here. So the thickness of the screen can be only a few millimeters. In fact, for OLED, it can be less than 1 millimeter, and that's why it can be loaded. So this is literally a revolution rather than evolution in display technology, going from the big and fat and heavy to thin and light. So the LCD was the dominant technology in the flat panel displays. It was discovered for the display technology. LCD is known for a long time, but for display applications, it was first discovered in RCA laboratories in the 1960s. First, by Williams, he basically observed that if you apply a voltage to an LCD liquid, it can get cloudy. If you apply voltage to it and we remove the voltage, it can be transparent. So just a optical phenomena, but you can distinguish whether it's light passing through or not passing through. And a few years later, George Hellmeyer took their inventions and make a clock out of it. And that's the first LCD clock that he made, and that is him in the 1970s, I suppose. For this invention, he was given the 2005 Kyoto Prize, just to make the connections. So the evolution of LCD took 50 years, as you can see in this timeline chart. It started with Williams and Hellmeyer's the discovery in the 60s, and there's other important discoveries, like the twist pneumatic, the liquid crystals by Martin Shade and Helfrich in the 1973, I believe. And then the active matrix backplane using amorphous silicon, also in the 70s. And around the end of 70 was the beginning of OLED. So we were behind by about more than 15 years. And then after that, you have the display development. You have the one important milestone was the development of the blue LED by Nakamura, Akasaki, and Amano. The three of them won the Nobel Prize a couple years ago for that discovery. And because you have the blue LED, you also can have the white, and so therefore they can use the LED as the backlight for LCD, and that was very important. And after that, there's different LCD display technologies, but mostly important but minor variations. The important development was that about the 2010, the Chinese in China beginning to make huge investment in LCDs, and the price drops as a result. And today, you can get a 65 inches LCD, at least in the United States, for about $500. So it's very inexpensive for a large entertainment technologies. So roughly that was the timeline of LCD. So you have some key developments, and also you have huge investment to drive the price down. So the evolution of OLED. This is mainly to challenge LCD, because LCD is quite a good technology and it works quite well for display. But it also has drawbacks. Otherwise, would not be able to overtake them. So what's the major difference between LCD and OLED display? So this is a picture of LCD. There are stack arrangements. It has multiple layers. The key is the LC layer in the middle, where you apply the voltage. It can turn the light, it's a shutter, so you can let the light go through, or you can shut it off. So LCD is a shutter. And you need a backlight. And the shutter is to shut off the backlight. And you have the other layer. The one important layer is the polarizer. You have two of them in the front and the back that allow the LCD to act as a shutter. So one of the major drawbacks is that the light is always on, the backlight, at least for the prior generation of the LCD. The newer generation, they can turn the backlight on and off depending on demand, all right? But we can, don't have to be concerned with that for now. But the biggest problem is that when you turn off the LCD, some light can still leak through. Okay, it's not 100% shutter. And this little amount of light that leaks through can degrade the image quality of the TV quite significantly. In other words, they cannot achieve a perfect black. For OLED, it's a light emitter. It has, at least conceptually, we only require 2 layers plus 2 electrodes and a support substrate. When you turn on the voltage, allow the current to pass through it, the LED, the device produces light. Okay, so when you turn it off, the light is off. So the contrast ratio, we call it the native contrast ratio, can be infinite, practically infinite. But the LCD, at best, may be 1,000 or a few thousands. And that is a difference. But that is enough that your eye can tell the quality between the two displays. And this OLED stands for organic light-emitting diodes. So where the organic coming from? So the traditional, conventional, the light-emitting diode is based on inorganic semiconductors, as you can see in the picture on the left. Basically a point light source coming from a very tiny chip, tens of micron on the square. So it's a point light source. It's a crystalline inorganic semiconductor. The application is for lighting, backlight for LCD, and also for the billboards. It's very defined application there. For the organic LED, it's an area light source instead of a point source. It's made of amorphous organic thin films. It can be used in smartphones, televisions, and wearable watches. So the real difference is that you can process the organic LED in an area. So that's why it's very suited for TV and flat panel display applications. And the fact it can be turned on and off very quickly is also a very important feature. So today's OLED display, the products ranging from televisions, you can buy 88 inches 8K televisions from LG for a very high price. There's also laptop made of OLED display, the tablet, and the most important application, it turned out, is in the cell phones. You also have application in the watches, the AR and VR applications as well. So from this figure, you can tell that OLED cover a very broad range of application. And that is one of the reasons it can be successful, just like the LCD. If you are only able to do the large area, or only able to do the small area, or only able to do one color, then you cannot cover such a wide range of applications. And on top of that, OLED has a very unique quality, which is, the display quality is excellent. So in 2013, the television was first introduced, the OLED TV. And this was me in front of LG's television. I'm not a salesman for LG. It just so happened that I was in a store in Hong Kong and they first introduced it. So I just went down there and take a look at the TV and I got a picture taken there as well. The price at the time was more than $10,000 when it was first introduced. But today, at least in the US market, you can get the same television for about $1,000. So it's a factor of 10 reductions in price over the last 6 years, which is quite remarkable for a display technology. And we look forward to further reduction in price in the OLED product in the future. So I want to show you what is in the future. And this is LG commercials. They loaned it to me. You can see a display coming out from a box. That is the box, and the display is coming out at a push a button. This is particularly good if you have a beautiful window in your bedroom or in your living room, and you just place that box right in front of your window, and you can look outside if you don't want to watch a TV, and then you can raise the TV if you want to watch it. The reason you can have this kind of new TV, because OLED is so thin, it can be rolled up. Also, OLED, because of thinness, it can be folded. So the the foldable phone in the market now, which sold by Samsung and Huawei, maybe a few others. So these two are products today, but they're kind of expensive. So now I'll go back a little bit to tell you a bit more about the discovery of OLED. The OLED was based on electroluminescence. The early work was done back in the 60s, just like the LCD. And in this paper here, published in 1965, the device was made of anthracene crystals sandwiched between the two electrodes here. And if you apply a voltage on the order of 2,000 volts, you can get a very small current on the order of 10 to the minus 5 amp per square centimeter, very small. But you can still see light coming out. And that's proof that the recombination of electron coming from the cathode and the positive charge coming from the anode, the recombination would give you light. And this is the evidence of it. And it was a blue light. So the first blue LED is actually organic, not inorganic LED, I think. But it requires high voltage and low current, even though the efficiency is high. So there's no applications. There's no practical applications. So here is how I came in. I spent a few years at Kodak when I first joined the research lab to work on organic solar cells. It was a total failure on organic solar cells in terms of applications. I did not make anything useful. But I did discover something quite important, and that is I can use a two-layer structure, or we call it the PN heterojunction structure, to enhance the photogeneration efficiencies, in other words, the solar cell efficiencies. The reason we could do that is because we have this junction right here. This is an energy level diagram I don't want to get into. That if you have anything absorbed in this region, the light absorbed by the materials would create excitons. And the excitons, can be dissociated by these junctions to separate the charge into holes and electrons, and that be collected in an external circuit. So it was a quite remarkable in terms of accomplishment at the time, because I achieved a 1% solar cell efficiencies, even though at the time the solar cell efficiency is more than 10%, based on inorganic semiconductors. But nevertheless, by the proper choice of materials, and with the thickness adjusted to about only 60 nanometer, I can get a very decent device performance. But only drawback is I get a 1% efficiency, competing with 10, 20% at the time. So the reason it was so inefficient, because the layer thickness is so thin. It doesn't absorb enough light, and that was the major problem. And I cannot increase the thickness because the transport of charges become a limitations. So I fail, and I move on. So I move on to organic light emitting diode. Based on the same structure, nothing changed. The same structure, almost the identical thicknesses. But now, I inject charges, instead of separating charges, and inject charges into it. Electron from the cathode, the holes, a positive charge from the anode. And the recombination takes place here, just because there's a barrier there that the charge cannot cross over. So they have to recombine. And the region for recombination, it can be so thin. So thinness doesn't matter. Actually, it helps because it requires lower voltages. All right. So because of that, and with proper choice of material, this is very important, proper choice of material. You cannot just randomly choose any material. You can get very high efficiencies. So with this bilayer structure, very thin films, and I'm also engineering a very important cathode, magnesium silver, and then you can derive very high efficiencies, I would say modest efficiencies, and at a low voltage. And another feature is that the very fast response. So it's perfect almost for display application with this kind of attributes. So this paper was cited over 16,000 times. It's quite remarkable. And just to give a little statistics, so the paper get published here, and then the number of citation goes up. And the regions that cited this paper, that China now, because there are more researchers that they're on this field, and it has the highest citation, followed by Japan and South Korea and the United States. This kind of reflects the development of the technology in that regions. And 2 years later, after publication of the first paper, I went ahead and come up with a scheme. We called it the doped organic thin films. What I did was that somewhere in this layer here, I introduced or inserted in the layer, which is doped with fluorescent materials. And this fluorescent material would be used to change the color coming out from the main emitter material that we call the host. And with this scheme here, we can produce green light and red light with higher efficiency and maybe even longer lifetime. But we were not able to produce blue light at the time because this host material can only generate green light. But the principle is useful for producing RGB. If you have a blue host, you can produce all three of them. So what my accomplishment, the contribution was somehow to make the electron-hole pair recombination to be more or less 100%. So every electron has to meet the holes. But then after recombined, you can go through two channels. One is called single channel, another one triple channels. So all my prior work was based on this single channel, which has only 25% efficiency, and that was the major limitations. And I wish I had found some way to utilize these channels, but I didn't. And of course, the other efficiency factor I'm not going to get into. The one milestone, another milestone paper that was published in 1999, almost 12 years after I published my first paper. And this by the group from Princeton and the University of Southern California, by these three gentlemen, Bortles, Forrest, and Thompsons. What they did is that they were able to use the triple channel, which has 75% pathway, so that together they can collect most of the recombination and turn it into excitons and turn it into light. All right. So they created a pathway forward to have 100%, we call it internal quantum efficiency. Every electron that comes in can produce light. And this is a major breakthrough. And that is also the reason why that we have the display technology today. Well, organic LED has some lifetime issues because it is emissive, and you go through the excited state, and not all the excited state will turn to light, and some of them can turn into degradation products. And so the OLED can degrade. You can drastically improve the lifetime without changing the materials. You're just changing the device architecture. Here we have Professor Junji Kyoto from Yamagata Universities coming up with a multi-stack structures, basically stacking each unit, all multiple units together in a series. So the current going through it, it would produce light in each of the unit, and the light would be summed to produce the light to go outside of the device. So this way, you can have little current going through it, but more light at the expenses of higher voltages. But this is a key development that enables the current television technologies. So what do we have? We have OLED, for the OLED technology, we have a low voltage drive, high efficiency now, full color using the doping scheme. Fundamentally, it's fast switching, much faster than LCD. High contrast because we can turn it off to have black as black. We also have wide view angles compared to LCD. We still have a little problems. The lifetime can be improved a little, but it doesn't prevent the technology to moving forward in commercialization. Like, for instance, we use the stack structure to improve the lifetime. So the evolution of display. So we felt confident that we can compete with LCD now. So, oh, I'm sorry, I forgot the sequence, but I'm going to take you through it. First, you have the iPhone. The iPhone measures about roughly 6 inches in diagonal. And within the screen, you have 8 million pixels, color pixels, and about 50 million transistors to operate this tiny screen, okay? And each color pixels can be switched on and off rapidly, and therefore you can see the images. And that's how complicated it is. But it all can be done monolithically, and that's why it can be made so cheap. You don't do it one by one. If you take one of the pixels and you blow it up, you find that all the multi-layer structures, your transistors there, the organics is there, and then you have the substrate, which can be plastic, and then you also have an encapsulation layer to prevent the oxygen and moisture from coming in. That's how you can protect the OLED. And each of the OLED stack, instead of consisting of 2 layers now, it consists more than like 5 or 6 layers. So it's very complicated, all right? And each layer has its own set of materials. And I'm showing here the 3 emitting material, red, green, and blue. It may not be the exact structure, but they're kind of complicated in molecular design, because you have to make sure they emit in the right wavelength and with the right bandwidth and so on. Okay, so there can be as many as 20 molecules, including the metal electrodes and other, in the stack. But they're all done by vapor depositions at this time. So I want to go through some of how we developed the display from very simple one to more complex ones. So back in the 1990s at Kodak, that we said that, okay, we have enough fun with the material development, let's try to make a display out of it. So we tried to make a very simple 100 by 100 display. And that means 10,000 pixels instead of 8 million pixels. So the simple way to do it is that you prepare the ITO electrode on the glass support, you and then you pattern it into rows, and then you put down the organic layer, and then you put down the cathode layer by evaporations, and then you do the lithography to pattern the top cathodes. It's easier said than done, because patterning the cathode can disrupt the underlying organic layer. So that was a problem, and the result that we achieved was not that good. The display was very defective, as you can see here. But that was in 1990. So a few years later, I came up with a way of patterning that doesn't require photolithography after we evaporate the organic thin films. We basically put the shadow mask on the ITO anodes before we deposit all the organic layer and metal layers. So organic layer and metal layer will deposit without the interruptions. And by evaporating the metal from oblique angles, we can produce a gap here, and a gap here. And therefore, we can isolate the cathode to give you the display. And Pioneer, the Tokuho Pioneer, took it one step further. They come up with a more elaborate scheme to isolate the cathodes, and they were even more successful. So they go with the process, and then they develop the very first passive matrix OLED. That is the very first applications using OLED display. Motorola use it for cell phone, and they also use it for the audios. So these are very simple ones. And now you have to move to the more active matrix display so that you can get a higher resolution, larger area, and so on. For reason is that if you use the simple passive matrix display, you're only limited to about a few hundred lines. With the active matrix display, what you incorporate the transistor with each of the OLED pixels, then you can infinitely scale it to 8K, 4K display, and that's how it move on. So back in the 1999, 2000s, we came up with a pixel scheme right here that not only for driving the OLED display that give you a very high uniformity. And so today, in your cell phone, you have 7 transistors, 1 storage capacitor for each pixels. At the time, we only have 2 transistors and 1 capacitor. Okay, so technology moving forward. So in Kodak, we had we developed the display. The first one is the 5 inches. Basically, we want to show it to the manager to impress them that we can actually make display. And we team up with Sanyo in this country here to make that. They provide the backplane, we provided the OLED technology. And the first product came out a few years later. In 2003, we used it for the phone, but unfortunately, it's very costly to make that display. So it's not a good business, so we had to withdraw that product. Making a product requires many, many people, and this is a small group of people in the research lab, trying to pull this off. And the person who really was in charge of this to drive the commercialization of OLED for Kodak is Dr. Rajaswani, and I just want to acknowledge him for his work. So, OLED display was introduced in the market. You have the cell phone, you have the TV. Here I want to show you the product that was proposed by 2 major corporations. One is Samsung, other one is LG. Samsung, here, the display quality is more or less the same. There's not a big differences. The Samsung chose a technology, we call it the LTPS TFT technology. And they also used shadow masking for patterning the RGB side by side. This approach led them to failure. So they commercialized it for maybe a couple of months and they have to put the product out. Simply because it's very difficult to use the pattern RGB technology to produce large area display. That patterning is not mature. And so as a result, they cannot produce panel cheap enough to make it. In contrast, LG has no problem that they use a metal oxide technology, and then they use RGB, using the white OLED, using conventional color filter to produce the color pixels. They take a hit in power consumption, but they can manufacture it. Okay, as a result, they are very successful in manufacturing, and they are the only suppliers, credible supplier of OLED TV today. So, in very short summary, I want to show you that in the first 20 years, I was very engaged in the material development, starting with my employment at Kodak, the OLED discovery later in that decade. This is the equipment that I use for making most of my devices. In 1987, the first paper was published. We make the first passive matrix display, the one I show you, that didn't look too good. And the other display, the older technology came in, like the polymer LED. And the Kodak, we also use the OLED for printing applications. The triplet emitter that enable 100% efficiencies didn't come in until 1999. And the phone The first cell phone was about 2000, and then from then on was the display technology developments. So in the next 20 years, okay, from 2000 to 2020, so we had the first micro display product, the Kodak camera, the Sony PDA, the first the so-called the smartphone, not the small cell phones, and the first OLED TV by Sony, and then the Samsung decided to mass produce OLED for their cell phone applications. And then the TV comes in 2013, and now the mass production starts in China. So if history is a guide, then you will be able to enjoy all the TV, cell phones at a lower price in the near future. Okay, this is the 88 inches television made by LG, and this is the rollable ones. Along the way, there's other development by other companies as well. So it has been a very fulfilling journey of a personal and scientific discovery for me, starting from a village in Hong Kong and ending in a discovery that leading to OLED. Along the way, I had the support of a very free, strong woman, my grandmother, my mother, and my wife. And I also have a wonderful family, and they're all here. Thank you very much.
Thank you very much, Dr. Kang. Please move to center of the stage to receive flowers.
Thank you.
それではタン博士にもう一度大きな拍手をお願いいたします。大変に我々の生活に結びついたお話をしていただきました。それでは次にご講演をいただきますのは、基礎科学部門で受賞されたジェームズ・ガン博士でございます。ではジェームズ・ガン博士、ご入場ください。それではご講演に先立ちまして、ジェームズ・ガン博士の横顔をご紹介いたします。スクリーンをご覧ください。
ジェームズ・ガン博士は1938年アメリカの南部テキサス州でお生まれになりました。子どもの頃にお父様がプレゼントしてくれた天文学の本を読んで以来、天文学者になりたいと思うようになりました。高校生の時には電子駆動装置を搭載した反射望遠鏡を作りました。この頃から将来は宇宙の観測、機器の開発、そして理論という3つのことについて研究したいとの思いが募っていきました。やがてカリフォルニア工科大学で天文物理学の博士号を取得しました。天文学の研究には天体の分布を記録した宇宙地図が必要です。1980年代には2次元のアナログ宇宙地図が使われていました。そこで博士は3次元のデジタル宇宙地図を作る スローンデジタルスカイサーベイというプロジェクトのビジョンを描き、自ら中心となって推し進めました。プロジェクトで使用された望遠鏡です。アメリカのアパッチポイント天文台に設置されており、2億3000万個の天体が記録されました。3次元地図に必要な奥行きを知るために、分光という方法で地球からの距離を観測しました。望遠鏡に取り付けられた光ファイバーケーブル一本一本が別々の天体を捉えるように設計されています。分光器につながる640本の光ファイバーで640個の天体が一度に観測できます。観測の効率が飛躍的に向上する画期的な方法でした。この方法を何度も地道に繰り返し、150万個以上の天体の位置を特定しました。これまでの観測とは桁違いの数でした。映像はこのデータをもとに作られた宇宙の3次元デジタル地図です。このプロジェクトで得られた膨大なデータは、数多くの発見を生み出しただけでなく、世界中の天文学研究の基礎的なデータとして役立っています。さらに博士は多くの宇宙物理学理論も発表し、大きな貢献を果たしています。こうして博士は観測、機器の開発、理論という3つの分野すべてでその中心となって研究を推し進め、歴史的な成果を成し遂げました。少年の頃から描いていた夢を叶えたのです。博士は人生を歩む上で誠実さ、寛大さ、愛情を持って生きていくことがとても大切ですとおっしゃいます。そして若い人たちへは、自分の強さと限界の両方を知ることが大事です。そして勇気と誠実さで限界を乗り越えてほしいとアドバイスをくださいました。京都について博士は、神社やお寺の美しさは見るたびに感動します。日本の心を感じますとおっしゃっています。
それでは本日はガン博士に宇宙物理学者としての人生を振り返り、広域観測を通じて明らかになる宇宙の物語についてお話をいただきます。演題は宇宙とそこにあるもの、広域観測を通して理解するです。それではジェームズ・ガン博士、お願いをいたします。
Thank you very much. I would like again to begin by thanking the Inamori Foundation and its founder for this prize and for the wonderful things it supports both in science and for the betterment of humanity. I'm very, very humble and grateful that the Foundation finds me worthy of this great honor. And now I would like to tell you a little bit about my early life and career, a little bit about how the Sloan Digital Sky Survey got started, and a bit about what it has found about the universe. You saw in the introduction a picture of me with my father. I was born in 1938. My mother was a quite gifted artist, but who decided to give up art for raising me. I'm grateful for that as well, of course. My father was a geologist, and he led a team during World War II to find oil for looking at places where the Earth's gravity was slightly low, and that indicated that there might be a pocket of oil below because oil is much less dense than rock. We moved around a lot as a kid, so I didn't really have a home. We would stay in a place about a year or so as my father moved from place to place. Because of the war, he had to become an expert machinist to keep his equipment up, and he taught me that skill, and that has stayed with me since. He died when I was 12 years old, and he was basically my friend. I had few friends because we moved around a lot. My teacher, my mentor, everything, and so it was quite bad. But I was interested in astronomy from the very beginning, really for as long as I can remember. I learned to read when I was fairly young, and the first book that I really remember, and certainly my favorite book, was a book called The Stars for Sam, which was written by a man, Maxwell Reed, for his nephew, a child. And he wrote a series of science books for children, and this book was published in 1938, the year I was born, and was a sort of major formative thing in my life. Once I read this book, I never really deviated very far from wanting to be an astronomer. I didn't have very much idea what astronomers actually did, of course, but I was interested in the stars, and I wanted to study the stars, and that stayed with me the rest of my life. My father was a geologist, but he was very interested in astronomy, and now he had a child to teach things, and so he had always wanted to build telescopes, and so we built little telescopes when I was a kid. And I was so taken by the subject that after he died, I continued to build telescopes. And when I was in high school in Texas, long after he died, I built this photographic telescope, which actually resulted in my first astronomical publications in about 1965. And so here is a picture of the telescope, there it is, the 8-inch telescope, and a photograph. It was an electronic drive, as the introduction said, and also had a camera. So I was able to take astronomical photographs, and I became very, very interested at that point in astronomical imaging and the state of the art in astronomical imaging. I was an undergraduate at Rice Institute in Texas. I majored in mathematics and physics. Did some research actually very early. This was in 1965. Computers were just coming along, were not used. They were used in business a fair amount, but were just beginning to be used in science. And I was lucky enough to get in at the very beginning of that and learned how to do scientific programming when I was yet an undergraduate. Graduate school, I went to Caltech in California. I wanted to do general relativity and went to Caltech to work with a man who died the summer before I arrived. So I was not able to work in general relativity, but became interested then in, I was still interested in observational astronomy, and was very interested in the universe in the large, and I became very interested in observational cosmology. That is, the cosmology is the subject of treating the universe as a whole, as an object, to try to understand how it expands and so on. I was very interested in Einstein and general relativity, and I did some work in gravitational lensing, which was quite important at the time. And also, about the time I was finishing graduate school, quasars were discovered. and it was thought that they were very, very far away. And I did some work with a fellow graduate student, Bruce Peterson, to look at the gas between the galaxies and the universe far away. And we were able to come up with an idea that you should or should not see this stuff, depending on exactly how it worked. And there came to be something called the Gunn-Peterson effect, which was not discovered for many, many years. And actually, it was the final thing was discovered by the SDSS much later, and we'll talk a little bit about that when we get there. While I was there, I continued to build instruments, both optical and electronics. And I became very interested in a particular aspect of cosmology, of the science of the universe, and that is how galaxies are distributed in space. Galaxies, as all things in the universe, gravitate, and so they pull on one another by gravity. And as a result, their distribution in space is not completely random, because where there are a few more, the gravity is a little higher, they pull and become even more. And so these clusters are one of the largest structures that we see in the universe. I did my thesis on this topic, and investigating something called the correlation function that says how much more probable, if you have a galaxy, is it that you have a neighbor than it would be if the galaxies were just strewn in space completely randomly. And this tells us a great deal about how the universe evolves and about how gravitation works on these very large scales. This is a picture, just a 2D picture, made from photographic data. This is of the southern sky, actually. So each dot in this picture is a galaxy. And you can see that the galaxies are not distributed randomly on the sky. You see clusters, you see groups, you see many, many things. All of this is the result of gravitation pulling galaxies together. This is simply a two-dimensional picture. If you add depth, and this was an early survey done at Harvard, the Harvard-Smithsonian survey, the depths are, the distances are color-coded, and so you can see that there's really very, very strong structure in 3 dimensions. And so I became very interested in making surveys that would do a better job. The statistics of galaxies in space, in order to do this well, is to do any statistical problem. If you're doing a sociological statistical problem, you have to have very large and very carefully chosen samples. And it's the same in doing statistical astronomy. Many astronomers spend their lives studying a few objects, a class of objects, sometimes only one object. And this is enormously important for giving us the depth of understanding in single things. But my emphasis was a little different. I wanted to study whole populations, to study the statistics, and to try to figure out, in the large, how the universe came to be the way it is today. This requires very, very large telescopes with very large fields, because if you want a big sample, you have to study a lot of sky, and that means you have to look at it, a lot of it at once. So you need very sort of wide field lenses in astronomy. And this is basically the story of my career for a very long time. 60 years ago, there wasn't very much in the way of surveys. There were small survey telescopes that made maps, partly for navigational reasons, partly just to find the locations of stars in the sky. But these surveys did not record very faint objects, and they didn't really allow quantitative interpretations of things, because it was just photography. Photography is beautiful, of course, to take pretty pictures, but it's very difficult to make quantitative measurements from. So all this changed actually began a long time ago, just as OLEDs began a long time ago before today. A fellow called Bernard Schmidt, who was a rather crazy Estonian optician, invented a camera that would make very, very wide fields in the sky, called the Schmidt camera or the Schmidt telescope. And there was a remarkable fellow called Fritz Zwicky at Caltech who realized the enormous impact of this on doing surveys. And Zwicky was one of the people who really pushed the idea of doing surveys. And he pushed very hard for a project to image the whole northern sky. And this was done with a Big Schmidt camera that he persuaded people to build. And it ended in 1957. It resulted in a product called the Palomar Observatory Sky Survey, or the POSS, which was photographs in red and blue light over the whole sky. He was a very interesting fellow. He's really one of my heroes in life. This is a picture of him, I think, in a kind of typical pose, and with the 18-inch Schmidt that he built. Zwicky didn't like astronomers very much. He thought all of his colleagues were fools, and there are many, many wonderful quotes from Zwicky, and this is, I think, one of the best of them. Astronomers are spherical bastards. No matter how you look at them, they are just bastards. But he is one of my heroes because of the emphasis on surveys. He also did really marvelous things early on. He predicted the supernova phenomenon. He predicted neutron stars. He knew that there was dark matter long before anyone else did. This is a picture of the 48-inch Schmidt that made the Palomar Sky Survey. So I want to step aside a minute from this general stream and talk about something which is very important for surveys. We have to have pictures, of course, to know where things are, but pictures don't tell us how far away things are. And in order to find out how far away things are, we need another tool. And the tool that we use is called spectroscopy. So let me spend just a few minutes talking about spectroscopy. One of the phenomena of light, of any kind of wave thing, is something called the Doppler shift. So if I have a galaxy that's moving, a star that's moving, anything that's moving, it compresses the waves, the light waves, in front of it in the way it's going. So the object is moving this way. You can see that this sphere of light was emitted when the object was back here, but the object has moved, and so the waves are compressed in the direction the object is moving, and they are stretched in the way the object is moving from. So if something is moving away from you, the wavelength of the light is longer, that's called, and its longer wavelength of light is red, that's called the red shift, and if it's moving towards you, the waves get closer together and moves to the blue, and that's called the blue shift. And we use this phenomenon to measure distances. The universe is expanding. We've known that for a long time. And what that means is that distant objects are moving away from us at very, very large speed. And the further away an object is, the faster it's moving. And there is a very simple formula that just says that the distance is some magic constant called the Hubble constant times the speed. And so if the speed is twice, the distance is twice. And that makes it very easy to sort things out in the universe. How do we do this? How do we measure the wavelength? Well, this is where spectroscopy comes in. We build an instrument which splits light into not just red, blue, and green, but into thousands of colors. And these individual colors tell us many, many things about the object, as we'll see. It makes a thing called a spectrum. The spectrum is just how much light there is at a given color of one of these thousands of colors. So the spectra of galaxies look like this. So here are three galaxies which are quite similar. This is the blue end of the spectrum, so this is blue light, that's red light. You can see that the objects at the top have a lot more red light. The objects at the bottom have a lot more blue light. You see several other things in here. Here you see a strong feature. That strong feature is repeated here, and it's repeated here, but it's at a slightly different place. That feature is the result of the absorption of light by calcium atoms. Well, that tells us something interesting, because it says that this galaxy, hundreds of millions of light years away, has calcium in it, the same calcium that we see on Earth. That feature is magnesium. That feature is sodium. So we see from these spectra what the object is made of. The fact that this one is shifted farther to the red than this means that it is receding from us more rapidly. That number is given by this redshift number here. We'll get back to that later. So this object is relatively nearby. This object is moving faster and is farther away. This object is moving faster yet and is even farther away. And so from this, we see what the objects are made out of, but we see more. This object is blue. This object is red. The blue comes from very young stars that were made only a few million years ago. This object has no stars that were made only a few million years ago. So these spectra tell us an enormous amount about the chemistry, about the history, and in fact, about the motion of these objects. So it tells us what the object is made of, how fast it's receding, and therefore how far away it is if it's out in the expanding universe, what are the temperatures of it, and also, if you think about it, the stars in these galaxies are in orbit about the center, and so some of them are approaching and some of them are receding. The result of that, there we go. The result of that is that if things are moving rapidly, these lines are broad, and if they're moving slowly, they're narrow. So we see not only how far away, how fast the thing is moving, but how fast things in it are moving with respect to one another. So we come back to surveys and how you do them. Photography it makes beautiful pictures, but it's not a quantitative method. And there was a lot of work, this kind of parallels what Dr. Tang told us about light emission. Astronomers don't need light emission. We need devices that record light. And there has been an enormous amount of work kind of paralleling, in a way, the work that he talked to you about light emission. Certainly photography would not have done this. We could not do a better survey with photography. We need new detectors. So in the 1970s, when I was at Caltech, Jim Westphal and I started working with a technology called CCDs that were developed at Bell Labs and that NASA were very interested in for space missions. We proposed and won a contract from NASA to build the camera, the first camera, for what was called just called Space Telescope then, that is now called Hubble. CCDs are very efficient, but at first, just as with the displays that Dr. Tang talked about, they were just too small. We needed bigger things. With the small CCDs, we built a camera called Four-Shooter. This is a picture of the Four-Shooter team on the 200-inch telescope at Palomar. The instrument is this big black thing in the background that you can hardly see. Here is Jim Westphal, my co-collaborator on Space Telescope, and a small team of people, of really excellent people, who built the instrument. So we needed something bigger. So in 1986, a fellow called Morley Blount that we had been working with at Texas Instruments moved to another company called Tektronix that was interested in making very big CCDs for things that didn't work out, but never mind, they made big CCDs. And Morley showed us this is a single silicon wafer, 100 millimeters in diameter, with a single device on it. And when I saw this, I knew that here was a way to do this wonderful survey that I had been wanting to do for most of my career. So let's build a camera, put a lot of these on one focal plane, and go from there. So this was the beginnings of the Sloan Digital Sky Survey. So I worked for a couple of years designing these things. I needed to design a new kind of telescope, actually, to use it. A big focal plane with many of these, many filters to obtain color data to get temperatures over as big a range as possible, and also to work on digital storage of the data, because if we had a lot of data and it was not available in digital form, it would not be very useful. But the survey would also not be very limited without spectra. But this big CCD was also a perfect device to serve as a detector for spectrographs. But if we want to do several objects at once, why would we want to do several objects at once? Well, when you break the light into all these thousands of colors, each color becomes very, very faint. And so it takes a very, very long exposure in order to record this spectrum A picture, there are only a few colors, and the colors are still pretty bright, and it doesn't take very long. So it takes much longer to get spectra. Just as an illustration, to do what Sloan did, suppose you wanted to take the spectra one by one with the telescope. The exposures are of the order of an hour each, 1 million galaxies, 1 hour, that's 1 million hours. At a very good site, astronomical site, there are about 1,000 dark clear hours per year, and with no overhead at all, but there's always overhead just making things work, it takes 1,000 years to take 1 million spectra. And I don't think any of us were quite ready to wait 1,000 years. But if you can do 500 at once, it only takes 2 years to do this. So the planning began for what became the SDSS. We had just joined an observatory, a new observatory building in New Mexico. The site seemed quite good for this, and we rather slowly and with difficulty obtained funding for this with a very large gift from the beginning from a fellow on the board at Princeton. And so eventually, the people involved in the Sloan survey were these, and I would like to bring your attention to this, a very, very large lot of work in the Sky Survey was done by the Japan SDSS promotion group. So Japan has been our colleague in this for a very long time. Why did it start then? Well, it really couldn't have started earlier because the technology simply wasn't there. We had to have the big CCDs. We had to have high efficiency optical fibers. I'll say more about fibers in a minute. That's how we get many spectra at once. And cheap and readily available computing to handle all these things. So the goals of the survey were to image, the whole sky is 40,000 square degrees, and to look up out of the Milky Way galaxy into the sort of clear part of the sky was to image the 10,000 degrees in the north, to classify and measure all the objects we could take pictures of, which was many more than we could take spectra of, about 200 million, to measure the redshift distances to the brightest million galaxies and the brightest 100,000 quasars, and to put this data together in a database that people could use. This picture you've seen before. This is just the Princeton team, but there were many, many institutions. Here is me and my wife, Jill, who played a very important role in the software in this project, a couple of our Japanese colleagues, and many others sitting in this room. So this is the site. The new survey telescope is here. You've seen pictures of it before. A nice picture taken at sunset. This is a picture of the instruments at the telescope. The two big green things are the spectrograph and the camera, which had 30 of these big CCDs, is in the center. This is a picture of the focal plane. There were 30 of these things, and they were arranged from red, green, two infrared, an ultraviolet filter and two infrared filters, so that we got, as a star went through this, we got data in all 5 colors in about 5 minutes. This is the distribution in the spectrum of the light from the ultraviolet, green, red, infrared, and farther infrared, and we recorded all of those basically simultaneously. Here is spectra. We did this by making a large aluminum plate, drilling holes at precisely the locations of galaxies that we learned from the imaging, plugging optical fibers in. The optical fibers come down, make the spectra, and go to the CCDs. You've seen this picture before. These are representative spectra from the survey. This is the sky that we covered, and you can see the dark is the main northern area. The green is a survey to look not at galaxies, but at stars. This was the data release at the end of the first phase of the survey, 8,000 square degrees, not quite 10,000, but we did the 10,000 in the next year. Photometry for several hundred million objects. Spectroscopy over 7,000 square degrees, 1.2 million spectra, and a lot of spectra of stars. So this is a kind of step through the survey. This is a picture with these bright things are put in by hand. They are the bright stars in the sky, just to sort of orient you on the sky. And what we're going to do is just zoom in, but we could zoom in to anywhere in this area, just as we're going to zoom in here. So we get closer. You can begin to see in the center maybe what we're heading for. This is called the Whirlpool Galaxy. So from that large area over the sky, one can focus and zoom in on any object you want in that large area. And there were many, many lovely objects we took pictures of. This is a picture of a globular cluster of a galaxy that is exploding currently. This stuff in the middle is not just a mist, it's gas being blown out of the center from a major explosion in the center. A beautiful spiral galaxy. A galaxy that has just suffered a collision with another galaxy. Galaxies don't always keep to themselves. They interact in very nasty ways with their neighbors. This is the nearest galaxy to us. This is Andromeda, the Andromeda spiral. And what I want to draw your attention to is this area. We're going to zoom in on it. This is just in one nearby galaxy. So we're getting closer. We're looking at a star formation region. This is gas, which is excited by hot stars in this galaxy. We come in. We also step way out in the universe. These are nearby clusters of galaxies. This is one in Coma, Hercules. And even farther, this group here is a group of galaxies at a redshift of about 0.3. That means about 30% of the way back toward the Big Bang in the system. And this is sort of at the limit. In this was just a single pass. We also did part of the sky, in which we did many, many times, so that we could add the pictures together. And you can barely see right in here anything, but clearly when we stack things together and make very long exposures, this is a cluster at about a redshift of 1, when the universe was about half its present age and half its present size. Lots of beautiful things in the Milky Way galaxy. These are all gas clouds in the galaxy in lovely colors. Now, this is the sort of 3D distribution. You saw the movie at the beginning. This is distance. So we're looking, this is just a thin slice of sky, looking at how the galaxies are arranged. And you can see that there are filaments, there are voids, there are clusters. It's a very complicated structure. How did this come to pass? Well, in 2001, this rocket was launched, which had a satellite, which made a map of the microwave sky. This is called the cosmic microwave background, the WMAP sky. The real distribution of this, it's almost completely uniform. The brightest things in here are about a part in 100,000 brighter than the coolest things here. But it is these little ripples in the early universe that made the structure we see. So we now know, and I really don't have time to go into how we know these things. The universe began 13.6 billion years ago. The universe is full of energy. And Einstein tells us that energy and mass are the same thing, in a way. And the things that we know about, protons and neutrons and electrons, is only about 4% of this. 25% is dark matter, and the other 70% is some dark energy that we don't quite understand. So let me say, if I go to a place where there is a very slight bump in the mass distribution and follow it, what happens is this. This is a bump in everything, in the ordinary matter and the dark matter. There's a lot of pressure in the early universe. It's very hot. And that pressure pushes the ordinary matter out, but the dark matter doesn't feel this pressure. So you see the ordinary matter, which is only a small part, going out. And the universe is cooling at the same time, and it becomes cold. And what's left is around every place that there was a bump, a hill, in the early universe, there is an extra distribution of matter. Can we find that in this? Yes. If we count galaxies, going out from the distance from a big galaxy, this is the correlation function that we talked about, you see that it drops off very smoothly, but there's a hump. So there are slightly too many galaxies in this ring. And this tells us that we understand pretty well what is happening in the early universe. Something else the Sloan did, because we had spectra of 1 million galaxies, we could easily look at their distributions. I don't have time to go into this in any detail, but this is colors, brightnesses, sizes, all of these things we can look at and look at the relations between. Let me call your attention to this picture. This is color versus brightness. These are bright galaxies, these are red galaxies, and let's look at that in a little more detail. So what we found was that there was a red sequence. These are the galaxies that we looked at that were red and not forming many stars, red and dead, they're called. There is a kind of green valley that separates these, and these are the blue things that are making stars like mad, even today. And so we want to understand how this developed from the microwave background and also how it developed and what we saw. We also studied the chemistry of galaxies. Stars make all of the things we are, the carbon, the nitrogen, potassium, all of these things are made in stars. And galaxies hang on to that gas when the stars explode. The stars explode, and that's how these things get out. Big galaxies, because they have high gravity, can hang on to this stuff. Little galaxies, these are big galaxies, these are little galaxies, are not so good at hanging on to it. And so there is a strong range of chemistry with mass. So the results of the SDSS, I think the ones I'm proudest of are these. We studied weak gravitational lensing. Gravitating objects bend light. And so you can study this, you can use this to detect directly masses in the universe, because you can look at how they bend light together. The baryon acoustic oscillations are what I showed you before, this pushing out of the ordinary matter. The properties of galaxies we saw. But also in the solar system, we discovered thousands of asteroids and looked at families of asteroids, chemical families, orbital families. We didn't really set out to explore the solar system, but we did. We found brown dwarf stars. These are objects which are between stars and planets. They don't burn thermonuclear fuel, and was thought for a very long time that they existed, and they were discovered actually before Sloan, but we found many, many of them and studied their properties. And of course, the large-scale structure of the universe. So the impact of this, as of the end of last summer, there were 10,000 scientific papers which used SDSS data. These papers were cited nearly 500,000 times. There were 1,000 papers with more than 100 citations, and 7 among the 100 most cited papers of all time. But it wasn't all we did. So there was also a very important legacy, I think, for the science. We insisted from the very beginning that the data would be made public very quickly, and we succeeded in doing that. And this resulted in the really natural growth of collaborations over the world using our data, both within the collaboration and without. And this openness is something that I hope it actually has become part of the sort of scientific sociology of astronomy, and it appears to be being a model for new projects. There was also citizen science. There was something called the Galaxy Zoo. We published a lot of pictures and asked the public to help us classify these things. We didn't even have any idea whether it would work, but within a day of the publication of this, we had 70,000 entries and over 150,000 people did this, worked on this as we went on. So that's sort of where we are and have been. The SDSS was finished some time ago. What do we want to do next? Well, it's very important to know that when we look out into the universe, we also look back in time. And so the universe is its own history book. if we can look out far enough, go faint enough to objects far away, we can study what the universe was like 1 billion years ago, 2 billion years ago, 10 billion years ago. And so the next step, I think, is to go out and be very faint. We know today that the universe actually is in its dotage, it's dying. This is a graph of the star formation in the universe, which is sort of the activity of things. This is a look-back time, so this is now. If we look back 10 billion years, 10 times as many stars per unit time were being born as are born today. So the universe was an incredibly active, noisy place compared to the rather quiet times of today. So we'd like to do a survey like SDSS, but with much bigger telescopes, to go much fainter, to study things far enough away that we can read this history. And it's happening. Japan is making it happen. There's a beautiful camera with 114 even bigger CCDs than we used, called Hyper Supreme Cam. Satoshi Miyazaki, who I hope is in the audience and is there, oversaw the building of this. This is a photograph taken at the commissioning of this instrument at the Subaru telescope. And the imaging part of the survey is underway and more than half complete. These are pictures of the instrument. It's very big. As you can see, here is a human being by comparison. This is the team that actually built the camera, and this is the focal plane with 114 CCDs in it. This is a picture that the telescope made. I think even on this screen it doesn't do justice, but you can see that there are very, very, very many galaxies. The galaxies almost overlap. So the faintest of these galaxies came at a time when the universe was only about 1/5 its present size and 1/5 of its present age. What about spectroscopy? Well, we have to have a spectroscopic component. We're working very hard on a spectrograph for Subaru that, again, will use fibers, this time many, many more fibers, 2,400 fibers, and it will reach ordinary galaxies out to the place where the universe was doing all of this really active stuff. And this instrument has been my focus for the past some years. I said the universe makes its own history book. It's hard to read because you have to go very faint. You have to have very sensitive instruments and go very deep in order for it to work. And we're doing our best to try to read this book. We, of course, I can't say that we're completely ignorant of it because surveys, small surveys, lots of work on smaller numbers of objects is going forward, of course, all over the world, but nothing like the size of the SDSS and nothing like the size of these surveys that we're talking about that Subaru is doing. So I would like to express my thanks not only to the Inamori Foundation for this enormous honor here, but also for the privilege of working with a very large and excellent group of Japanese astronomers since SDSS days. And now, you know, I was part of running the SDSS, but they have taken over and are doing a very much better job with very big telescopes. I should also say, and I did not say really sufficiently, that you saw the list of institutions for the SDSS. I was project scientist for the SDSS, but the work I did was 1%, some tiny fraction. All of that work was done by my colleagues at these institutions, and especially wonderful for me was that the work was mostly done by my younger colleagues. So we old guys and gals who ran the survey, and we did a pretty good job, but the science was mostly done by the young colleagues, and they did a wonderful job. And that continues in the project today, and I am enormously proud of that. I was kind of the father of SDSS, but it was my children who did the work. So thank you all, and thanks especially to the Inamori Foundation.
Thank you very much, Dr. Yang. Please move to the center of the stage to receive flowers.
Thank you.
ジェームズ・ガン博士、ありがとうございました。それではジェームズ・ガン博士にもう一度大きな拍手をお願いいたします。皆様ありがとうございました。それではここで休憩といたします。再開は3時5分でございます。3時5分の再開とさせていただきます。よろしくお願いいたします。
ご案内いたします。お席を立たれる際はレシーバーを座席に置き、お戻りの際は元のお席にご着席いただきますようお願いいたします。またお帰りになられる方はレシーバーを座席に置いてお帰りください。なおご協力いただきましたアンケートにつきましては、受付付近の係員にお渡しください。Ladies and gentlemen, please leave your receiver on your seat when you leave. Before you go, we would greatly appreciate it if you would cooperate to fill out the questionnaire and hand it in to the staff member at the reception on your way out. Thank you. ご案内いたします。まもなく再開いたします。会場にてご着席の上、お待ちいただきますようお願いいたします。繰り返しご案内いたします。まもなく再開いたします。会場にてご着席の上、お待ちいただきますようお願いいたします。Ladies and gentlemen, the Kyoto Prize commemorative lectures will be resuming shortly. Please return to your seat. The Kyoto Prize commemorative lectures will be resuming shortly. Please return to your seat. Thank you. ご案内いたします。 まもなく再開いたします。ご着席いただきますようお願いいたします。Ladies and gentlemen, the Kyoto Prize commemorative lectures will start soon. Please be seated. Thank you.
お待たせいたしました。それでは講演会再開をいたします。次が本日最後の講演ということになります。講演をしていただきますのは、思想芸術部門で受賞されましたアリアーヌ・ムヌーシキンさんでございます。それではムヌーシキンさんにお入りいただきましょう。どうぞ。それではご講演に先立ちまして、ムヌーシキンさんの横顔をご紹介します。スクリーンご覧ください。
アリアーヌ・ムヌーシュキンさんは1939年、フランス・パリの西に接するブローニュ・ビアンクールという町でお生まれになりました。お父様は著名な映画プロデューサーで、ムヌーシュキンさんは幼い頃から芸術に接する機会の多い家庭で育ちました。1950年代後半、イギリスでオックスフォード大学演劇協会や実験演劇クラブに参加したり、フランスでパリ学生演劇協会を結成したりと、本格的に演劇の道に進んでいきました。そして1964年、仲間と一緒に太陽劇団という劇団を結成しました。1960年代、自由と平等を求める政治社会運動が世界中で起こりました。文化芸術の分野でも新たな潮流が生まれ、演劇の世界でも旧来的な表現の方法や仕組みを打破しようとする動きが高まりました。ムヌーシュキンさんと太陽劇団はこの革新的な動きの中で登場し、多くの人々を触発する存在として常に注目され続けてきました。舞台制作にあたってムヌーシュキンさんは、演劇とは何か、いかにあるべきかを徹底的に捉え直しました。その考え方を演劇の世界に存在してきた演出家、俳優、裏方スタッフの間にあった階級的な考え方と構造を取り払い、集団創作という方法を取り入れてきた太陽劇団という劇団で実現しています。さらに俳優の身体を重視し、即興の演技を活用しながら世界の伝統芸能を演劇の要素に大胆に取り入れるなど、独自の創作を実践しています。そして歴史上の出来事や現代の極限状況を主題として取り上げることで、人々が自らの歴史や社会と向かい合い、見つめ直す機会となる作品を送り出しています。50年以上にわたって演劇の第一線に立ち続けているムヌーシュキンさんは、今もなお世界各地を訪れ、現地の演劇人たちとの交流を続けています。ムヌーシュキンさんは、愛、信頼、自信、この3つの言葉を若い人たちへ送りたいとおっしゃいます。京都の印象について、美しさと静けさと調和、そして女性たちの隠された苦難、この苦難こそ私が溝口健二の映画や近松門左衛門の芝居から学んだものですと おっしゃっています。
それでは今日はムヌースキンさんに自らの演劇創作の始まりと人生について人や場所、作品との出会いから語っていただきます。演題はこの賞は誰に贈られたのかです。それではムヌースキンさんお願いいたします。
Otaru, Morinoki Hostel, 4 septembre 2019. 40 minutes. Mon discours doit durer 40 minutes. Une éternité. Pour le public, pour vous, qui êtes censés à la fois percevoir par les changements de mes intonations la sincérité de mes propos, et en comprendre le sens en écoutant Fumiko-san, l'interprète émérite chargée de vous les traduire. 40 minutes, mais ça fait au moins 10 pages. Et encore, si j'examine les discours de certains de mes prédécesseurs, cela peut aller jusqu'à 15 pages, même agrémenté de traits mystérieux graphiques ou de photos d'enfance. 40 minutes, vu la simplicité de ce que moi j'ai à vous raconter, c'est très long. Comment les vivre et les faire vivre, ces minutes interminables, ces minutes qui seront irrespectueuses, martyrisantes, si pendant qu'elles s'égrènent, je vous ennuie. Ce qui est pour moi et pour toute femme ou homme de théâtre un péché mortel. Ennuyer. Quelle horreur. Vous faire souffrir alors que vous êtes tous venus si aimablement pour honorer le choix de la Fondation Inamori, c'est-à-dire nous, les 3 lauréats de cette année, Dr. Ching W. Tang, Dr. James Gunn et moi, Ariane. À Paris, le 31 juillet 2019, j'avais déjà choisi en épigraphe « We are such stuff as dreams are made on ». De quelle étoffe est donc faite la lauréate d'un aussi majestueux prix que le prix Kyoto? Qui m'a tissé? De quels rêves, de quels innombrables rêveurs suis-je issue? Qui m'a engendré? Qui sont ceux qui, bien avant et bien plus que moi, eussent mérité ce prix? Ces innombrables lauréats possibles, glorieux ou anonymes, comment les évoquer? Comment leur rendre justice? De quel lait, de quel pain ai-je été nourrie? Qui a pétri ce pain? Sur quelle terre a poussé ce blé? Qui l'a moissonné? Sous quel soleil? La France, bien sûr, mon pays bien-aimé, m'a protégée la plupart du temps, soignée et éduquée. Mais avec elle, quels sont les pays qui m'ont cultivée, m'ont inspirée? À qui dois-je d'être moi? Sur quelle multitudineuses traces dois-je partir pour exprimer ma gratitude, ma frustration ou mon effroi parfois? Toutes ces pistes qui mènent à mon petit moi imparfait, mais qui, comme pour tout être humain, dessinent un réseau planétaire, ce sont elles que je vais devoir retrouver pour écrire ce discours. Ce discours qui m'intimide tant, mais dont l'effrayante obligation a la vertu de me pousser à cette enquête et à cette reconnaissance. En me l'attribuant, à combien de centaines, peut-être de milliers de femmes et d'hommes avez-vous en vérité donné ce prix bienveillant et somptueux? Aujourd'hui, ces privilèges, ce luxe, ce raffinement, cet entourage affectueux, à qui les dois-je? Aux sueurs, héroïsme, dévouement, constance, génie et illumination de qui et de combien? Combien de combats et de morts a-t-il fallu pour que moi, femme, épouse d'une femme, je vive libre dans un pays presque en paix, que j'y fasse librement du théâtre et reçoive un tel honneur? Et monsieur Inamori, qui en versant sur mon théâtre une pluie d'or salvatrice, me somme de faire mieux encore, que veut-il? I have decided to create the Kyoto Prize as a means of recognizing persons who have made outstanding contribution to the progress of science, the advancement of civilization, and the enrichment and elevation of the human spirit. Those worthy of the Kyoto Prize will be people who have worked humbly and devotedly, sparing no effort to seek perfection in their chosen profession. Their achievement will have contributed substantially to the cultural, scientific and spiritual betterment of mankind. Perhaps more importantly, they will be people who have sincerely aspired through the fruits of their labors to bring true happiness to humanity. Mais se rend-il compte de ce qu'il dit? At the very last, I hope to honor these people and thereby to motivate them and others like them to reach still greater heights. Se rend-il vraiment compte de ce qu'il demande, cet homme admirable? Ses souhaits, ce paysage de bonté humaine venu d'un autre siècle, proféré par un homme qui, du fait de son activité professionnelle, ne peut ignorer la pente férocement cynique que notre monde d'aujourd'hui dévale, c'est le cas de le dire, à tombeaux ouverts. Ces vœux sont le signe d'une telle force d'âme, d'une telle enfance préservée, que nous ne pouvons que rester ébahis et bouleversés. Rappelez à l'ordre, en quelque sorte. Oui, ce prix est un rappel aux ordres de nos rêves. Mais enfin, ai-je vraiment fait cela, monsieur Inamori? Ai-je vraiment sincerely aspired to bring true happiness to humanity? Je crois que j'ai souvent, très prétentieusement, espéré le faire. Nous, femmes ou hommes de théâtre, nous pensons tous que nous devons bien être utiles à quelque chose, que les histoires que nous décidons de raconter, ou qui, plus exactement, décident d'être racontées par nous, seront utiles, qu'elles seront éclairantes, nourrissantes, indispensables. Nous pensons que la transformation formelle que le théâtre exige pour devenir théâtre entraîne forcément la transformation, l'élévation des âmes que l'humanité demande pour devenir vraiment humaine. Certains accordent ce pouvoir à la prière. Otaru, 5 septembre. Tous les soirs, juste avant d'aller ouvrir la porte de notre théâtre, je rappelle aux jeunes femmes et jeunes gens qui viennent nous aider à servir les repas des spectateurs: mesdames et messieurs, attention, attention, notre théâtre va ouvrir. Et quand je suis très gaie, je dis même « Attention, attention, notre beau théâtre va ouvrir ». Et tout le monde sourit derrière le bar. Quand parfois un événement extérieur nous a angoissés, et Dieu sait si nous avons eu à Paris ces dernières années des événements angoissants et cruels, j'ajoute, je vous rappelle que nous avons charge d'âme, et me murmure à moi-même, comme toujours. Avoir charge d'âme et en être conscient. S'engager à avoir charge d'âme les uns, à avoir charge des âmes les uns des autres. Ne serait-ce pas, après tout, un projet politique et social suffisant? N'est-ce pas ce que liberté, égalité, fraternité veut vraiment dire sur les frontons français? N'est-ce pas ce que M. Inamori imaginait en créant ce prix si ambitieux? Mes amis et moi, nous savons que l'œuvre que nous produirons sera d'autant plus digne, plus artistique, plus belle, que les conditions dans lesquelles elle aura été enfantée, car il s'agit d'un fantastique accouchement, que ces conditions auront été aimantes, ferventes, passionnées, confiantes, et si, embarqués que nous sommes toutes et tous, actrices, acteurs, techniciens, administrateurs, administratrices, co-directeurs et moi-même, sur cette barque fragile et périlleusement secouée qu'est un spectacle en devenir, si nous aurons pris soin les uns des autres, si nous nous sommes fait confiance, si nous avons espéré le meilleur de chacun d'entre nous, bref, si nous nous sommes aimés. Pour cela, il nous aura fallu, et sans vouloir attrister cette si belle assemblée, il faut bien que j'en parle, il nous aura fallu résister au désenchantement du monde d'aujourd'hui, à sa froideur, à son manque absolu de sens et de forme, à son conformisme économique implacable. Ce conformisme économique assassin, imbécile, chanté et argumenté par ceux-là même qui devraient le dénoncer. Y résister âprement et nous en protéger. Je nomme là ceux qu'on honorait autrefois du très noble titre de serviteur de l'État et que parfois ne méritent plus que celui de laquais des gouvernements. Bon, il me faut revenir à cette étoffe mystérieuse dont vous et moi nous sommes tous faits, œuvre de tisserands innombrables, célèbres ou ingratement ignorés. Il m'appartient aujourd'hui de tenter d'en reconnaître quelques-uns sans que cela devienne une liste assommante. Là, évidemment, je le sais, il faudrait que je vous parle de mes parents, de mon enfance. Je souhaite à toutes les filles d'avoir un père comme était le mien. Bien qu'il fût inquiet pour l'avenir de ses deux filles, bien qu'il me prodiguât toutes sortes d'avertissements sur les difficultés du métier que très tôt j'avais décidé de faire, jamais il ne m'a donné le sentiment que quelque chose me serait impossible si vraiment j'y mettais le prix, c'est-à-dire la passion, l'effort et la confiance. Comme nous nous sommes querellés, lui et moi. Au moins tant qu'il fut fort et en bonne santé. Jamais après qu'il eut son anévrisme, je voulais faire attention. Mais la dispute nous manquait. N'être d'accord sur à peu près rien et nous aimer totalement. J'étais de gauche, il était plutôt à droite. Il avait fui l'Union soviétique en 1923. Sa famille, juive, avait tenté de vivre sous le joug bolchevique, mais en vain. Il avait réussi à fuir en France, il avait 15 ans, avec presque un enfant, avec sa petite sœur. 2 ou 3 ans plus tard, ses parents arrivèrent à Paris. C'est une longue et extraordinaire épopée familiale qui ressemble à celle de milliers d'émigrants russes, mais qui ensuite, pour Alexandre et Tamara, mes grands-parents, ressemble au massacre de millions de Juifs à Auschwitz. Sans tout à fait comprendre le fonctionnement égalitaire de notre troupe, peut-être même en le désapprouvant, il était malgré tout très fier de moi. Moi, je trouvais les films qu'il produisait parfois trop commerciaux. Il me traitait de snob et me rappelait que j'étais bien contente de recevoir l'aide financière qu'il pouvait me donner grâce à ces films trop commerciaux. Il avait raison, j'avais tort. J'espère pouvoir le lui dire un jour. Il m'emmenait avec lui sur les plateaux de cinéma. Cela sentait le caoutchouc chaud des câbles électriques, la poudre et les crèmes des actrices. Il y faisait torride à cause des énormes projecteurs de l'époque. Tout un monde étincelant, sensuel. Les actrices étaient très belles, les acteurs très gentils. Et puis un jour, après le bac, tu dois parler mieux anglais. Ma mère était anglaise, mais mon anglais n'était pas digne de l'Angleterre. Hop, on m'envoie, avec mon consentement, ravi, passer une année scolaire universitaire à Oxford, à St. Clair's Hall, au coin de Lathbury et de Banbury Road. J'y apprendrai l'anglais, bien sûr, mais surtout, béni soit le théâtre universitaire britannique, j'y commencerai le théâtre et ma vie allait s'y décider. Ensuite, un voyage au bout du monde allait entériner cette décision. Otaru, Morinoki Hostel, 6 septembre. Pourquoi ai-je tant de mal à imaginer faire pour ce discours ce que certains de mes prédécesseurs ont si bien fait, une autobiographie? Pourquoi me paraît-elle si simple, si insuffisante même? C'est parce que, au fond, je sais que mon Bildungsroman, mon roman personnel d'initiation, n'a été qu'un chemin en quête de compagnons de route, de travail, de vie, d'amitié, d'amour, d'aventure, de rêve et de révolution positive. Je pressentais, je savais que je ne ferais rien toute seule. Sauf peut-être voyager un moment, justement pour m'exposer à la froidure et à la peur dans la solitude d'un voyage qui, lui aussi, fut destinal et initiateur. Alors, le voyage. J'ai apporté mon billet. Il s'agit de mon billet Marseille-Yokohama sur le cargo mixte, le Cambodge, de la Compagnie des messageries maritimes. Départ 30 avril 1963 du quai numéro, c'est devenu illisible. Première escale, Port Saïd, l'entrée du canal de Suez. Oui, on prenait le canal de Suez. Les 3 grands lacs qu'il relie étaient encore, à l'époque, parsemés des épaves de navires bombardés au cours de l'expédition colonialiste, catastrophique et idiote, qu'avaient menée la France et la Grande-Bretagne avec l'aide d'Israël pour tenter de récupérer le canal que Gamal Abdel Nasser avait eu l'audace de nationaliser au nom du peuple égyptien. Je traversais l'histoire. Escale à Aden, puis Bombay. Le bateau entre dans le port. Une odeur de mangue et de merde m'arrive du marché voisin. Le soleil se lève, les corbeaux semblaient vouloir attaquer le bateau. Pour la première fois, je mets le pied sur le sol indien. Je suis dans le mythe et la légende. Lors de cette escale, je ne verrai que la magnificence. La face sombre, je la subirai au retour. Le grand amour avec ce pays, continent, je le vivrai plus tard. Colombo, Singapour, Saigon, en pleine guerre du Vietnam, Hong Kong, Kobe. Arrivé à Yokohama, le billet ne promettait rien, mais le trajet avait duré 30 jours. Donc nous sommes probablement arrivés le 1er juin 1963. Il pleut. C'est le déluge. Il pleuvra ainsi pendant 2 mois. Oh, comme j'ai détesté le Japon pendant ces 2 mois. Je ne parlais évidemment pas japonais, et les Japonais, en 1963, chez eux, ne parlaient évidemment rien d'autre. Même les signes, les mimiques, qui me paraissaient les plus clairs, provoquaient des yeux ronds et un refus effrayé de tenter même de les comprendre. Oh, comme j'ai détesté les Japonais pendant ces 2 mois. Et puis, une fée est apparue. Marcel Juliaris, un journaliste français, parlant parfaitement le japonais, marié alors à une japonaise. On disait en ce temps de ce genre d'amoureux fins connaisseurs du Japon qu'ils étaient tatamisés. Marcel est enfin revenu de Corée, m'a prise sous son aile, rassurée, orientée, et grâce à lui, j'ai commencé vraiment mon voyage dans ce pays dont la culture théâtrale et cinématographique allait devenir pour moi une initiation et une inspiration permanente. Un de mes maîtres, les autres seront l'Inde, Bali, Meyerhold, Jacques Copeau, et je m'en expliquerai plus tard, mes compagnes et compagnons de travail. Oh, comme j'ai alors aimé le Japon et les Japonais, et cela pour toujours. Un jour, avant le retour de Marcel, de Corée, désespéré et sous la flotte incessante, j'errais à pied dans le Tokyo incompréhensible de 1963. Le Tokyo qui se préparait à son grand retour pacifique sur la scène mondiale en organisant les Jeux olympiques qui allaient avoir lieu en 1964 et qui furent un immense succès pour la ville et le Japon tout entier. Cette préparation consistait, me semblait-il, à détruire tout ce qui ne l'avait pas déjà été par les bombardements américains. Tout ce qui restait de la guerre, ou avait même été reconstruit depuis 18 ans du Tokyo ancien, je le voyais, stupéfaite, disparaître de jour en jour. De si beaux quartiers en bois s'évanouissaient en une nuit. De beaux immeubles du 19e s'effondraient, eux qui avaient échappé à la destruction guerrière. C'est d'ailleurs ainsi que Ichikawa Kon commence le film magnifique qu'il fut chargé de faire sur ces jeux mémorables. Une énorme boule de béton est balancée contre une façade. Celle-ci tombe droite, face contre terre, presque en silence, comme un résistant stoïque abattu par un peloton d'exécution. Depuis, partout dans le monde et dans mon propre pays, je me pose sempiternellement la question: pourquoi, pour progresser, devons-nous vraiment détruire tant de paysages urbains ou naturels, si chers au cœur de leurs habitants et si précieux à notre harmonie intérieure? Pour éviter autant que faire se peut ce que George Orwell appelle le progrès destructeur, ne devrions-nous pas user de plus de discernement et d'humilité? Est-ce réactionnaire que de poser la question? Ne devrions-nous pas réfléchir avant de faire moins beau, moins humainement vivable, plus dévorateur d'énergie et de ressources? Je déambulais donc, je l'ai dit, désespérée et seule en ce Japon qui ne ressemblait pas encore à mes rêves. J'arrivais, mon gros guide touristique détrempé à la main. qui m'indiquait que lui et moi avions probablement atteint tout à fait par hasard le temple de Sansoji, dans le quartier appelé Asakusa. Il y avait effectivement un immense temple devant moi, mais ma mauvaise humeur me le fit ignorer, et je continuais à avancer à travers de petites rues qui, malgré la pluie, étaient très animées. Inconsciemment, je me laissais guider par une musique qui semblait m'appeler jusqu'à, dans une ruelle, l'entrée minuscule et très colorée de ce qui ne pouvait être qu'un théâtre. Minuscule, lui aussi. Mais d'où jaillissait cette musique? Était-elle sonorisée ou pas? Je ne me souviens pas, mais c'était très puissant. Mais bien sûr qu'il s'agissait d'un enregistrement, puisque, une fois à l'intérieur, Otaru, 7 septembre, une fois à l'intérieur, je ne vis qu'un seul acteur, un jeune acteur, qui allait, à lui tout seul, donner un sens à mon désespoir japonais, à ma solitude, à la pluie, au déluge, à tout mon voyage. Oh, que ne puis-je vous donner son nom, le remercier, et devant vous, partager le Kyoto Prize avec lui. En un après-midi, ce garçon m'ouvrit les terribles portes du royaume des acteurs. C'est ce jour-là, dans cette salle minuscule, à demi pleine de vieilles dames attentives et enamourées et de vieux messieurs impénétrables, que je compris pour toujours ce qu'était un vrai acteur. Seul en scène au début, les yeux fixés sur un horizon inquiétant, parce que je l'imaginais peuplé d'une horde d'envahisseurs à cheval, approchant rapidement. Il nous parlait, il criait, je ne comprenais rien, mais je voyais tout. Son regard affolé me faisait voir les yeux tout aussi affolés des chevaux écumant sous les fouets et leurs sabots soulevant la poussière ou déchirant la prairie, faisant voler des mottes noires comme des bombes. Il alertait le village, c'est sûr, et pour mieux le faire, saisi d'une inspiration soudaine, il traîna sur sa petite scène un immense tambour. Était-ce celui du temple qui, sans aucun doute, était en coulisses? Toujours est-il qu'il se mit à battre un tocsin, à faire dresser tous les chevaux de votre assemblée sur vos têtes et à soulever les paysans les plus apeurés ou endormis. Il était le prince Hal, il était Hotspur, il était Falstaff, Macbeth devant la forêt qui marche, Henri V, il était Shakespeare. Ce jour-là, pour la jeune voyageuse ignorante que j'étais, dans cette misérable petite salle de rien du tout à Asakusa, grâce à un humble acteur japonais, il n'y avait plus ni Japon, ni Occident, il y avait le théâtre universel, humain et grandiose. Il était merveilleux, ce jeune homme, probablement chef d'une troupe de... Dans mon ignorance, j'appelais cela petit kabuki. Mais ce n'est que beaucoup plus tard, en fait tout récemment, qu'en allant assister à une représentation de la troupe de Daigoro Tachibana, j'appris que ce style se nommait Taishu Angeki, qui se traduirait en français par théâtre pour le peuple, théâtre populaire. Rendez-vous compte, moi qui toute ma vie ai aspiré à faire mériter ce titre magnifique de théâtre populaire au Théâtre du Soleil. Il y avait eu d'autres illuminations. Avant l'accostage final à Yokohama, le Cambodge avait fait escale à Kobe, où, par un hasard merveilleux, j'avais pu voir le soir un eau en plein air, éclairé seulement par d'immenses brasiers. J'étais retournée à bord, chancelante, foudroyée par la puissance, la splendeur, la majesté d'une telle forme. J'escaladai la petite échelle qui m'avait servi à grimper sur ma couchette depuis un mois, dans un état d'exaltation juvénile indescriptible. Un monde merveilleux allait s'ouvrir à moi. Je ne pourrais plus jamais dormir. La rencontre avec l'acteur inconnu d'Asakusa me confirmait cela. Otaru, 8 septembre. La métaphore dont j'usais et use toujours pour parler de la troupe que j'ai fondée en 1964, après ce fameux voyage, était celle du navire, de la barque, de l'esquif, dont, oui, je l'avoue, je me voyais plus comme le capitaine que comme le mousse, mais dont je savais qu'il ne voyagerait loin que si chaque membre de l'équipage se sentait valeureux, magnifique, épanoui, même dans le danger, et malgré les sacrifices que, je le savais, cette épopée allait nous demander au début. Au début seulement, croyais-je. Je sais aujourd'hui qu'elle exigera le meilleur et le plus profond de nous-mêmes jusqu'à la fin. Rien n'est acquis. L'amour, l'amitié, le respect du public se cultivent tous les jours. Un manquement est toujours ressenti comme une trahison, car c'est une trahison qui efface des années de dévouement et de succès. C'est peut-être injuste, mais c'est ainsi. Quand en 1959, bien avant tout cela, après cette répétition fatidique de Coriolan au Playhouse Theatre d'Oxford, je monte m'asseoir à l'étage de ce bus rouge, numéro 2 ou numéro 3, fonçant dans la nuit pluvieuse de ce mois de décembre, et que, tremblante autant que lors d'un coup de foudre amoureux, je décide, ou une divinité décide pour moi, que je vais faire du théâtre. Il s'agit d'art, bien sûr, de l'art théâtral que je vais devoir explorer, pratiquer et apprendre tout au long de ma vie. Mais il s'agit aussi d'un petit peuple, un échantillon de monde que je veux créer et réunir autour de moi et entraîner dans cet élan amoureux. Il s'agit aussi de politique, d'exemple, d'utopie. Il s'agit d'un récit minuscule, mais fondateur. Je compris très vite qu'il allait me falloir des compagnes et compagnons très courageux et confiants, car Epina Bausch décrit très bien cette même intuition ici, lorsqu'elle reçoit l'honneur que vous lui fîtes en 2007. In the rehearsals, I was afraid to say I don't know or let me see. I felt obliged to say, okay, we'll do this and this. I planned everything very meticulously, but soon realized that I was also interested by a completely different thing that had nothing to do with my plans. Little by little, I gave up planning. Since that time, I have been getting involved in things without knowing where they will lead. C'est exactement ce qui m'arriva. Je compris très vite que la position du metteur en scène omnipotent, prévoyant tout, et soi-disant totalement maître du sens et de la forme, ne me suffisait pas. Je voulais plus. Je voulais que tous, nous profitions du talent de tous. Je voulais que tous, nous apprenions les uns des autres. Bon, cela voulait dire traverser des déserts inimaginables. Cela voulait surtout dire que les acteurs allaient entendre une parole terrifiante et insolite dans la bouche d'un, et encore pire, d'une metteuse en scène, cette parole étant « je ne sais pas ». Qui n'a pas suivi des répétitions de théâtre ignore probablement l'effroi, la tétanie ou le sauf-qui-peut généralisé qu'un tel aveu peut provoquer chez des acteurs qui n'auraient pas été prévenus de cette possibilité, pour ne pas dire de cette méthode. Morinoki, 9 septembre. Et puis, dès le début, il y avait eu les fées à moustache, les fées un peu chauves, les vieilles fées courbées par l'arthrose, courageuses et visionnaires, issues du Conseil national de la Résistance, Jeanne Laurent, Jean Villard, qui devant nous tracent le chemin lumineux du théâtre national populaire, un chemin artistique, politique et surtout moral. Le Festival d'Avignon, celui d'alors, le vrai, Paul Puot. Il y avait eu Arnold Wesker, qui nous donne les droits de la cuisine, son plus grand succès, en vérité, son triomphe, alors que nous ne sommes encore qu'une minuscule troupe de petits amateurs. Et c'est ce spectacle qui va nous mettre au monde. Et puis, Paolo Grassi, fondateur avec Giorgio Strehler du Piccolo Teatro di Milano. Il nous y invite, il nous accueille, il nous permet d'y triompher avec 1789. Le soir de la première, je le revois encore, perché sur un des balcons du Palalido, l'immense stade couvert dans lequel nous jouions, en chemise et en bretelles, avec son ventre tout rond, en sueur, dansant sur la musique de la prise de la Bastille, si heureux de notre succès. Ah, nous lui devons tant. Dans le si simple et si émouvant discours qu'il fit ici même pour la même occasion, Kurosawa Akira dit, en parlant de Jean Renoir et de John Ford, qui, soit dit en passant, font aussi partie de mon panthéon, et qui leur accompagnait un soir, après un bon dîner français à sa voiture. « What nice people they were, I thought. They were warm-hearted, generous, and had the power to embrace people. When I get old, I thought I want to become like them. » Même si je les considère de la race des géants, race dont je ne suis pas, moi aussi, je veux être comme eux quand je serai vieille. Car nous avions besoin de ces gens au cœur chaleureux et sans crainte, capables de nous accueillir, capables de nous embrasser, parce que sans crainte, ils ne nous voyaient pas comme des rivaux encombrants, mais comme leurs enfants ou leurs petites sœurs ou petits frères. Et les jeunes créateurs d'aujourd'hui ont les mêmes besoins. Eux à qui on répète tous les matins qu'ils sont trop, trop nombreux, trop chers, pas assez rentables, que leur modèle économique est irréaliste, voire nocif à notre époque. Mais de quel modèle économique la société d'aujourd'hui peut-elle donc être si fière, alors que de l'Irak au Chili, les peuples contre lui se soulèvent pour prétendre à l'imposer à de petites bandes d'artistes qui veulent, eux, pratiquer un modèle moins pathologique, moins destructeur des âmes et des corps. Otaru, 10 septembre. J'écris à grand-peine ce discours, pendant que des nouvelles m'arrivent d'Europe, ou plutôt que je vais fébrilement les chercher. Le Brexit. Des salopards continuent leur manipulation assassine. La Grande-Bretagne, la mère des démocraties, est ébranlée par un clone du président actuel des États-Unis d'Amérique. Le démagogue ignare qui dirige le pays le plus puissant du monde a trouvé son petit double anglais, moins ignare, mais aussi forcené, grossier, menteur. Et tous les deux s'acharnent à coups de mensonges, de cynisme, d'irrespect des lois de leur propre pays ou du monde, non seulement à démembrer le Royaume-Uni, mais à saper l'Europe, une des plus étonnantes réalisations politiques de l'histoire des hommes, imparfaite, certes, mais extraordinaire. Je vous en prie, permettez-moi ce qui peut vous paraître une digression inutile au Japon, en l'occasion d'aujourd'hui, mais qui est inévitable pour une femme de théâtre dont la source n'est rien d'autre que le monde qui nous entoure. Comment ne pas saluer la volonté inébranlable, titanesque, de quelques grands hommes de tous bords politiques, anciens ennemis jurés, qui, après les deux guerres qui fracassèrent le monde et le XXe siècle, surent, bridés, bâillonnés, enfouir les haines anciennes et accomplir cette œuvre géante. L'union de 28 pays parlant 24 langues, allemand, anglais, bulgare, croate, danois, espagnol, estonien, finnois, français, grec, hongrois, irlandais, italien, letton, lituanien, maltais, néerlandais, polonais, portugais, roumain, slovaque, slovène, suédois et tchèque, sans compter quelques 60 langues régionales. Grands et petits royaumes, empires, duchés, républiques, qui pendant 2 millénaires n'avaient eu de cesse que de s'envahir, de s'étriper et de se martyriser les uns les autres contre tout intérêt réel des peuples, contre toute compassion et sagesse humaine, avaient enfin, très laborieusement, et je le répète, très imparfaitement, commencé à réfléchir ensemble à la paix des peuples européens, c'est-à-dire en partie à la paix du monde. Et pendant que je tente d'écrire le message que j'ai promis d'écrire dans la douce petite ville d'Otaru, sur Hokkaido, deux clowns délinquants s'étant éphémèrement saisis de l'outil si noble mais si fragile de la démocratie, prétendent s'en servir pour ajouter aux maux de l'univers et redéchirer ce que le temps, aidé d'hommes et de femmes sages, avait su recoudre. Otaru, 11 septembre. Attention, ne pas se laisser détourner de mon message, de l'étoffe dont nous sommes faits, de tous ceux à qui, outre l'acteur d'Asakusa, vous avez donné, sans le savoir, ce prix que je reçois aujourd'hui. Dans mon adolescence, il y eut d'abord le cinéma. Paris, où j'ai eu la chance de vivre dès 1948, est encore une ville cinéphile. Tous les films y passaient, et en version originale, ce qui est le vrai signe de l'amour du cinéma et des acteurs. Comme je le disais, il y eut Renoir, John Ford, George Cukor, Capra, Minelli, Hitchcock, Stanley Donen, Gene Kelly, Griffiths, Lillian Gish dans Le Libus brisé et dans Le vent de Victor Sjöström. Il y eut La nuit de chasseurs de Charles Laughton. Il y eut Vittorio De Sica, Rossellini, Visconti. Et puis, Déflagrateur, Sancho Daioux, Les contes de la lune vague après la pluie, Les amants crucifiés. Bref, il y eut un des grands empereurs du cinéma mondial, Mizoguchi Kanji. Puis l'autre empereur, Satyajit Ray, l'Indien, avec La complainte du sentier, Le monde d'Apu, Le salon de musique. Puis déferlèrent les 7 samouraïs, Kagemusha et tout Kurosawa. Mais lui, Dieu merci, vous l'avez distingué à temps. Il y eut un astre à part, Charlie Chaplin. J'ai puisé dans ces trésors, sans scrupule, consciemment ou inconsciemment, un peu comme tous les dramaturges communs ou immenses ont puisé goulûment dans le banquet homérique, puis dans Échille, puis dans Shakespeare, puis dans la Commedia dell'arte, puis dans Molière, puis dans Tchekhov, puis dans Meyerhold, puis dans Brecht. Il y a Victor Hugo, il y a Dickens, il y a Chikamatsu Monzeamon pour tous les maîtres de Bunraku et de Kabuki. Il y a Dostoïevski, bien sûr. Il y eut Orwell. Il y eut Vie et destin de Vassili Grossman, pour moi le plus grand livre du XXe siècle. Et il y a, je suppose, pour vous, avec qui je parle ce soir, beaucoup d'autres que dans l'émotion j'oublie aujourd'hui ou qui me sont inconnus ou, par ignorance, me sont indifférents. Ce sont des hommes sources, des hommes océans. Nous, les petits nains qui nous baignons dans leurs eaux généreuses et vivifiantes, nous sommes les débiteurs éternels. Otaru, 12 septembre, je me réveille ce matin sans courage ni inspiration. Alors que je ne suis que dette, je sais déjà que j'ai omis des femmes et des hommes célèbres ou humbles qui ont eu une influence sur mon destin et donc sur celui de mes proches et donc sur mon travail. Travail que vous couronnez aujourd'hui. J'ai failli oublier Jacques Lecoq, je vais en oublier d'autres, Dulin, Jouvet, mon Dieu, qui d'autre encore? Il faudrait que nous soyons capables d'un discernement quotidien surhumain pour pouvoir noter chaque soir dans un cahier sacré le nom des fées bienveillantes ou des anges gardiens salvateurs rencontrés ce jour-là. Et ce, bien avant même de savoir écrire. Pour moi, je pense qu'ils furent innombrables, dès mon enfance. Depuis le policier français qui, pendant l'occupation de la France par l'armée nazie, n'a pas rempli le formulaire que lui fournissait la Gestapo pour retrouver June Hannon, ma mère, Alexandre Mnouchkine, mon père, et l'enfant Ariane. Jusqu'à Mademoiselle France, institutrice, hors cadre, hors système, qui m'apprit à lire en faisant de cet apprentissage une traversée enchantée, quotidiennement, furieusement désirée. Je pleurais de rage quand on ne m'envoyait pas à sa petite école. Elle inaugura une lignée de quelques professeurs merveilleux dont les ombres sont ici, autour de moi, pour recevoir ce prix avec moi. Sur ce cahier sacré, je devrais pouvoir vous dire toutes celles et tous ceux qui, par leur aide, leur exemple, leur réprimande ou critique légitime et amicale, m'ont rendue meilleure ou en tout cas moins mauvaise. Toutes celles et ceux qui, par leur combat, leur héroïsme, parfois leur mort, m'ont enjoint d'avoir le petit courage de ne dire que ce que je pense vraiment et de n'emboîter le pas ni céder à aucun dogme, fût-il entonné par des milliers et soutenu par des millions, tant que je n'étais pas absolument sûre que telle était ma conviction morale et profonde. Toutes celles et ceux qui ont paré des coups qui m'étaient destinés, toutes celles et ceux qui m'ont gratifié d'un sourire, d'un regard confiant, d'un compliment sincère, toutes celles et ceux avec qui j'ai ri de moi, de nous, sans crainte et sans reproche. Rire de nous-mêmes, ensemble, signe irréfutable de l'amitié. Et vous savez quoi ? Toutes celles et ceux qui nous ont donné ou prêté de l'argent. Oui, de l'argent. Ce fluide qui circule dans les veines de tous les systèmes de production, et cela, que nous le voulions ou non, pour un bon moment encore. Peut-être devais-je dire pour encore un mauvais moment. Bref, au cours de ces 55 ans d'existence, des gens nous ont donné de l'argent. Ils doivent savoir que nous savons que dans ces circonstances, leur argent représente quelque chose de bien plus noble que lui-même. Il représente leur respect, leur compréhension, leur amitié, parfois même leur amour. Et surtout, comme ce Kyoto Prize, il nous met au défi de faire mieux. Et cela me mène à vous parler de mes grandes rencontres vivantes. Bon, c'est long. Otaru, 23 septembre. Je vous disais plutôt que je considérais le groupe de mes collègues de travail comme un de mes maîtres. Ils furent mes plus sévères et affectueux garde-fous, et ils le sont toujours. Pourquoi ? Parce qu'ils savent que je ne sais pas. Ils savent que dans les diverses obscurités que traverse notre aventureuse Smala, ma petite lanterne de chef caravanier est intuitive, certes, perspicace, souvent, mais éteinte, parfois. Dans ces cas-là, que ne ferait-on pas pour avancer quand même, quand le chemin intérieur semble bouché, comme il est tentant d'user de l'habileté histrionesque acquise et de passer par l'extérieur, par le semblant, le faux semblant, par la réplique qui tape, la scène qui cogne, ou encore, pire et beaucoup plus fréquemment, par cette rouerie cérébrale virtuose en dérobade qui prétend déguiser l'impuissance en intelligence, le vide en profondeur et faire passer du rien pour du nectar intellectuel. De cela, je fus préservée, d'abord par mes goûts naturels, qui sont simples, certains les disent naïfs, mais aussi et surtout par les sourcils froncés et les regards incrédules de mes amis comédiens et comédiennes à la moindre glissade de ce genre que j'aurais eu la mauvaise idée de m'autoriser. Jamais ils ne me laisseront oublier le courage qu'il faut pour prendre le théâtre de front. Aucun sommet, même de l'Himalaya, n'est déclaré atteint tant qu'il n'a pas été conquis par la face la plus raide. Le théâtre du peuple se prend comme ça, frontalement, par sa face la plus raide. Théâtre ou pas théâtre? That is the question. Et pour tous, la réponse est visible, audible, sensible, pour ne pas dire sensuelle, concrète pour tous. Il faut du courage, du souffle, beaucoup d'humilité, de la patience et des mollets. Je veux dire un corps respecté et reconnu comme outil majeur de l'art de l'acteur. Bon, tout cela est bien bon, mais comment vous parler de celles et ceux qui ont fait ma vie et qui la font encore? Comment vous les présenterez autrement que par l'abstraction sèche d'une liste de noms? Car une fois nommée Hélène Sixou, une immense écrivain, en quoi vous aurais-je éclairé sur la profondeur de notre relation dans la vie et dans l'art qui pour nous sont mêlés? Que saurez-vous de plus sur la dette incommensurable que j'ai envers elle, qui m'a tant appris et m'apprend encore? Une fois nommé Jean-Jacques Lemaître, un immense musicien de théâtre, que saurez-vous de plus sur le rôle essentiel, fondamental, que tient sa musique depuis 40 ans dans mon travail? Une fois nommé Martine Franck, Guy-Claude François, Erhard Stiefel, Charles-Henri Bradier, que saurez-vous de plus sur ce que je leur dois? Une fois nommée Giuliana, mon épouse, que saurez-vous de plus sur ce qu'elle est pour moi? Cette tribu, cet équipage, cette famille turbulente, cette petite galaxie du Soleil, composée comme toute galaxie de grands astres lumineux, de planètes plus modestes, de lunes, de comètes et même de météores, comment vous faire partager l'estime, l'amour et la reconnaissance que je ressens pour elle? J'aimerais que vous connaissiez au moins certains de leurs visages. Certaines, certains, les fidèles, vous verrez, on voit le temps passer dans leurs cheveux et sur leurs fronts. Certaines, certains ne sont plus de ce monde terrestre. Il y a aussi nos enfants qui grandissent de spectacle en spectacle. Mesdames et messieurs, permettez-moi de vous présenter ceux à qui vous avez décerné le prix Kyoto pour les arts et la philosophie 2019, le Théâtre du Soleil. Ça, c'est le tout début, 1789, à la cartoucherie. Les saluts, les fondateurs. « 1970. Et ceux qui ne sont plus avec nous. Martine, très grande photographe, ma meilleure amie. Philippe, le bon acteur. Roberto, notre premier décorateur. René Patrignani, un immense acteur. Germinal, très grand danseur. Ursula. Andrés Pérez, qui est devenu un grand homme de théâtre au Chili ensuite. Guy-Claude. et Bernard, celui qui a fait la lumière de tous nos films. Ceux de maintenant, Hélène, Sixou, Jean-Jacques Lemaître, Charles-Henri Radier, le co-directeur, mon double. Hélène. Eh oui, c'est à cet âge-là qu'elle a commencé avec nous. Maurice. Giuliano. Nirupama, qui nous est venu de l'Inde. Duccio et les enfants. Ève. Charoyer, qui nous vient de Perse et de France. Dominique et Sébastien. Et toute la suite que je vous laisse regarder. Georges, Andrés et Georges, Myriam, Clémentine, de nouveau Andrés, Simon et Giuliana, Simon, Catherine, le cœur des Atrides, Tartuffe, Montis et Myriam, Renata, au Tibet, Delphine, Serge, Olivia, le spectacle, nous sommes venus jouer chez vous à Tokyo. Madame Lee, et ceux qu'on ne voit pas d'habitude. Erhard Stiefel, le sculpteur de masques. Victor, Antonio, Hector, Jean-Claude à la couture, Sophie, Pierre, Pedro et Naruna, Maria. Et le bureau actuel. Astrid. La couture, Marie-Hélène et Nathalie. Annie. Hervé et Martin à la technique. David au bois. Étienne partout. Virginie à la lumière, Geoffroy à la lumière, Pascal, Karim, certains acteurs afghans qui aident à la cuisine et au bar. Elsa, lumière aussi. Elena, notre peintre. Hélène et Étienne, au bout. Thérèse et Marie-Lou, musiciennes. Anne-Lise. Daniel, notre peintre. Yann et ses oreilles, c'est le son. Didier. Certains de nos professeurs, Jacques Lecoq, Kim Duk-soo, un immense musicien coréen, Samandam, notre maître de Terukutu, et Maitreyi, qui nous aide tellement. Thomas et Alexandre, Julien, Duccio et sa fille, Albagaï, Sarah, Amalia et ses copines, Iraj, Dionisio, Galatea, Lucien et Iraj dans la forêt qui marche. Et notre acteur japonais, Ono-san, Armand, Vincent, Annamelia, Judith, Ijayan, Alice, Sylvain, Maxence, Astrid, Siar, un jeune acteur afghan. Et ça, c'est le jour où nous avons appris que nous avions le Kyoto Prize. Merci infiniment.
Thank you very much. Thank you very much. Thank you very much, Mr. Swarovski. Please move to the center of the stage to receive for that. Manuski-san, ありがとうございました。では、マニスキーさんにもう一度大きな拍手をお願いいたします。以上をもちまして第35回京都賞記念講演会を終了いたします。長時間ご清聴ありがとうございました。会場内に段差などございます。足元には十分お気をつけいただきたいと思います。本日は誠にありがとうございました。
ご案内いたします。ご使用になられましたレシーバーは座席に置いたままお帰りください。またご記入いただきましたアンケートにつきましてはお近くの係員にお渡しください。繰り返しご案内いたします。ご使用になられましたレシーバーは必ず 座席に置いたままお帰りください。本日はご来場いただき誠にありがとうございました。お気をつけてお帰りください。Ladies and gentlemen, thank you for your attendance today. Please leave your receiver on your seat. Before you go, we would greatly appreciate it if you would cooperate to fill out the questionnaire and hand it in to the staff member at the reception on your way out. Please make sure you have left your receiver on your seat. Thank you again for joining us today, and we wish a pleasant evening.